This is alternative to rope embeddings, so let's understand this path attention paper, and this will help us understand attention mechanism more deeply and move us towards overcoming transformers and attention mechanism with the next big architecture. I read it and I understand it, so I'm gonna use Gemini to help me explain it. If we have a sentence cat sat on mat, we need to know the order of words. So right now, what's popular is using this rope, rotary positional embeddings. But rope only shows how much distance is between tokens. So for example, if we look at token mat, this token is 1 place away, 2 places away, 3 places away. So when we calculate attention between mat and cat, we just know it's 3 places away. But we don't know that this cat is actually sitting on this mat, so we don't take any information from like these inner tokens or about like what's happening. We just calculate attention between these two based on their similarity and how distant they are from each other, but not based on like the entire context. So instead of just calculating attention between mat and cat, PaTH is also gonna add information from these in-between tokens. So attention is calculated better based on the context. So this is how PaTH will do it. So this cat will produce a key, and key is a vector that it's just a compressed version of this token cat that explains what information this cat holds. So the key, it doesn't hold information itself, it just says what information it holds. It's a description of the information, so it's a lot smaller vector than this cat, the full cat token. And by the way, you already know this if you know attention. So this is the key from attention mechanism. This produces key, this produces query. But then we take that vector, key vector, and we will actually modify, change it a little bit, because this key vector has some semantic meaning. So this dot, this vector spot, that vector goes from origin to this spot, this encodes some semantic meaning. And if we change this vector a little bit, we're gonna change the semantic meaning. So this vector key for the token cat, we're gonna change it a little bit with this set to encode the meaning that the cat was sitting, and on that to encode the meaning that cat was sitting on something. So starting from the key for cat, we're gonna change a little bit, move a little bit to encode set and a little bit to encode on. So now this key will actually have information from all of these in-between tokens as well. And then we multiply that key with the query of the mat to find their similarity. So PaTH is encoding both position and semantic information of these tokens, of this context in between. But why are we just encoding context in between tokens? Why not tokens before cat? I didn't really get this. So maybe if first author of this paper, Song Lin, is watching, maybe she can explain. And I will pin her comment if she wants to explain anything else on top of the YouTube, below the YouTube video. So just to recap, we have a key of the token cat. We're gonna modify the key a little bit based on this. So we will multiply something from here with the key to just move it around a little bit, and then we will take that result and multiply with something, we'll see with what, from on, to move it around again. And now we have key that encodes both position and semantic context. And I'm gonna leave this explanation and everything in my Discord below in this PaTH attention in Learn AI Research under my YouTube tutorial lessons. Now let's look at this word set. So we need to extract some information from this word set and then use it to multiply, to modify this key of this word cat. So we can give context from this set into the key of cat. So first we need to find, so imagine this set as a vector embedding. It's just vector embedding, this token. So we need to kind of find which part of this vector embedding, which part, meaning like which direction, which part of this, if we decompose this vector embedding, which part should we give to the key cat that is gonna influence. So we don't need to give entire vector embedding set. to the word cat. We just need to maybe give a part that explains that the action of sitting. So imagine that this set is a vector embedding, and some of the dimensions in that vector embedding are actually for actions. Maybe some of the dimensions are for colors, but we don't have any colors, that has anything to do with this. So maybe those dimensions with colors, for colors, are not important in this token set. So in this token set, only the dimensions that describe the action of moving, sitting, doing this, doing that are important. So how do we just extract information from the vector embedding about these actions and then add that information to the word key of the cat? Now, taking that token embedding of the word of the token set, we will have some learned weights. Those learned weights are same for every token, and they are learning to extract important dimensions, important features from every token embedding. So when we multiply any token, for example word set, with these learned weights, they will actually just extract important features, for example the action. So here the action of sitting is important. Okay, it's not important some dimensions that have color, that have fur, that have being alive or not, that's not important. Or those are close to zero, they don't have any information in this word set. So from this token set, we will generate two things. One is vector W and beta scalar. So vector W is just those important components that describe the action in this case. So vector W is just a vector that describes like the action of sitting. And it's smaller than this whole token set because that actually can describe a lot more things. So we just need the action of sitting and then to append that, to give that information to the cat. So the cat is sitting. So we don't need all of the information, we just need this small bit of information about sitting. So cat is sitting. So W is the new vector calculated from the token embedding set that's just gonna show the action of sitting. And beta is how important this action is to our token cat. So in this case, cat is sitting. It's actually quite important because this tells us what cat is doing. And it's important to the both cat and mat. So we know that cat is sitting, so it's important. So beta will be bigger. But for this token on, this is maybe less important than the word set. So maybe here beta will be smaller because this is less important. So we don't want to take so much information from this word on. We don't want to modify this cat because it's not so important. It will maybe just ruin or cause some noise or issues, changing all of the information. To recap, from each token in between, we create two things. Vector that extracts information, for example, information of sitting, so we can add it or multiply this cat with this sitting vector that shows action of sitting, so we can add that information. And beta that shows how important this extracted information is. So sitting information is more important than information from word on. So beta here on will be smaller, and we will add less information from this word on to this word cat. And the way we get that extracted information, the W vector and beta importance, is we have learned weights for both of them that just transform token embedding in one set of weights transforms it into W vector, and the other set of weights transforms it into beta importance. And those transformation weights are same for every token. And they will just produce different W and beta based on the token itself, but the weights are same. Now let's see how Gemini explains it, maybe even better than me. So the W vector is what and where tool. Think of the high-dimensional space of word meanings. Different directions in this space represent different concepts. For example, action, direction, sentiment direction, location direction. So W is this direction vector that points in the direction of a specific semantic axis. And each of the axes can be, one axis can be just action axis. So maybe if we are on this side, we are running, moving fast. Maybe on this side, we are sitting, going slow, or not moving anywhere. And then token set might generate a W vector that points along this action axis. So when you multiply this W vector with the cat, it will only change part of the cat vector that's on this movement axis, action axis. Here you can check this. So let's say we have this is the word set. This green is our W, our direction that we want to. So next step, we will project our token set onto this W direction. And we have a very long projection, which means that this token set has a lot to do with this axis of action. And so we will use then this projection to modify the key. So this requires some self-study. You can find materials below this video. I'm gonna leave you all of the links. You can use this video to study with your self-studying. So we need a formula that's gonna project our set token onto this direction W that we calculated. Let's go step by step on what happens. So let's say we have a token for the word set, which is, let's say, this token. And we have W, so these are weights. These are weights that generate our W direction. So when we multiply these weights with the token, we get our W. But we need to normalize this just to make the numbers nicer between 0 and 1, or close, or just maybe maximum a little bit above 1. So neural networks likes these smaller numbers between 0 and 1, minus 1. So anyways, we just apply L2 normalization. That's not important. Intuition here, the word set has created a transformation axis, which is going to be this, that focuses on the second and third dimension, our made up action dimensions. So we suppose that second and third are about actions. So then other dimensions are not important. They are 0. Then calculate beta, which is how much the strength. So intuition behind beta is set is an important word, so it gets a very high strength beta, close to the maximum of 2, which is 1.78 right now. It will cause major change. So the way we calculate it is we take again our token x2 set, and we have some learned weights and bias to get some number in the end. We need to pass that through sigmoid as well here. So this is it's like a single neuron. The whole thing is a neuron that gets us value at the end. So now we need to construct this transformation H2. So this is the final transformation that we will apply to the key. So we will multiply H2 matrix times the key to transform the vector, the key vector. And then for the next token, we will multiply its transformation H3 with the result. So H3 at H2 at vector. So we just have a line of these transformations that are transforming the key. The formula is identity matrix minus beta, which is, okay, I'll tell you why identity matrix, but let's see this. We have beta, which shows the strength of our transformation, the strength of how much H2 will influence the key vector when we multiply it. And W, our direction, but we have W times W transposed, which is actually our projection onto the, so that's gonna give us a projection, this red line. So W times W transposed times this X will give us the projection, this red line, onto this W, which is the green line. So again, we have this green, which is this small W direction. We say W at W transposed, and then multiply that with this X vector to get a projection onto this. Guys, I made a mistake. This X is not actually our sitting, our set token. It just shows how to project a vector onto a direction. If I say that this vector X is our set token, just ignore that it's not. And then we will scale this projection with beta. How important, how much of this we want to modify the key. So this part is for giving us the projection, and this part is for strength, how much we want to reduce this projection when we later multiply. So this red will stretch or suppress this dimension of our cat. This requires a bit of self-studying. Actually, it's confusing to me a little bit. So basically, you can look at this age as stretching or squishing this dimension of movement or sitting inside of the vector cat. So this age 3 is the transformation from the word set that we will apply to the key of the word cat. And let's just decompose this. I said the formula for age is identity matrix minus beta for this token times W for this token times W transposed. So we will multiply all of that with our key. Let's decompose this. So key can actually multiply just this I. So this will give us the key matrix itself, because this is identity. So this will just be K. And here we have beta times this projection of the K, which is the key matrix, onto this direction W. So this is the projection of the K matrix onto the direction W. Projection of the key vector, vector, not matrix, onto this direction W, which is this green direction, and this red is the projection. So this red is what you get when you multiply this. So let's look at the two parts. This I times K is just the original vector, K, and then this beta times this projection, the scale projection. This part projects the vector K key onto the what axis W of the token. So in this case, what axis is our movement or sitting axis. It finds the shadow or component of K that lies in that specific direction. So we just extract this component of the K. We extract K component that's about sitting. So we extract information about sitting from the key, from the cat. So we want to see if cat is sitting or not. So we extract that information from the cat itself by projecting the vector cat onto this W direction of the movement of sitting. And now it shows how much the cat is actually sitting or moving, which is this red vector that shows us that. And then beta will scale this information. So what we do is W projection takes this action, like sitting or walking or standing, and then beta makes it stronger or weaker. So if this direction red says that, like, if it's longer, it means the cat is walking slower or sitting. So then we want to make beta stretch this even longer to show that cat is actually not moving, not sitting. Or if it shows that it's going fast, then we want to reduce this vector, strength of this vector, to show that actually it's going slower sitting. So beta will lengthen or shorten this a particular dimension within cat based on the token set. So to recap, we use token set to find which dimension in the word cat it's influencing, for example, movement. So we use that with the W. And then we use beta to stretch that dimension or to reduce based on the movement and based on what that dimension is actually showing. So I'm gonna leave these URLs below, these chats. There is a bunch of chats. So I recommend you just press Ctrl F and search for these words if you wanna find the specific point of explanation. And join my Discord. I just made a new Discord where we kind of research LLMs. So we want to research efficiency. For example, if you don't know what to research, this is a project for you. I want you to test PaTH versus Rope for our Blueberry LLM. So this is the plan. You can modify the plan. You can then create a report and we will help you. And this is a piece of actual research you would do, and you would contribute to open source, and you would hone your skills, and you would contribute to our project. And there is a lot more research projects here. This is like an open source online institute that we're gonna build. So we're gonna do a bunch of research here for open source. Everything is fully open and you can learn, and there is like courses here, learn AI research. There are courses, and we can you can also create your own tutorials, because for me, tutorials help me learn. And then you can participate in official research projects, which we have 2 for now. And you can create your own projects and research projects, or find other people's research projects as well. I'm gonna get like PhD students and actual professors from good universities to join us. I already know some, and we're talking. And they're gonna share their research, and you're gonna be able to learn from like top university researchers and PhD students and professors and scientists once they join. So right now, I just made this yesterday. So we just have a few people, but now I'm gonna start making videos about it. So I call this like online AI research institute, Blueberry AI. And we wanna be competitive with OpenAI, XAI, Anthropic, everybody. And okay, so that's it. Thank you for watching, and see you next time.